Okay. So guess we probably don't have the connection from the other end. Well, let's get started. So okay, so far I think we've covered basically most of the essential components of mathematical optimization techniques and some interesting engineering application domain. And we don't have the new homework assignment, I guess, beyond what I have been posted on Blackboard. So next week, there will be no homework assignment due, I guess. And I intend for some of you to think about what you want to do for the term project so that you can maybe write me a 1 to 2 page description of what you plan to do. Of course, you can first take a look at the assigned topic that I already posted on Blackboard, which is also a very interesting problem to explore and also sharpen your skill in using MATLAB and optimization toolbox, including the so-called convex optimization CVX software package that you can also install, download and install from the link I posted on Blackboard. Okay, so I guess we've talked a lot about optimizing decision variables, which are continuous and discrete, and also local methods for doing the optimization, finding a stationary solution, finding the local optimal, and then the global optimal. And also, I think the most challenging part is when we shift the gear from continuous decision variable to discrete ones, things become less clear what you can do. And I think in the homework assignment, we have this so-called branch and bound technique for some small-scale problem. You can probably figure out what would be the optimal solution by enumerating all the possible configurations for both discrete variable x2 and x3. But in real life, you have to rely on some computer algorithm to avoid exhaustive search. On the other hand, there are some efficient algorithms that can handle discrete optimization problem. In such a particular case, I think we've talked about dynamic programming, which I hope some of you still recall is based on the idea of what? I'm sorry? Of decompose the objective function into multiple stages and then what? And then do some calculation on what? On each stage, where basically you don't have to enumerate all the possible states. You need to calculate some kind of cost to go, and then what? Something like the cost accumulated so far to reach that state. And then, of course, if the number of possible states can be maintained in a finite number, then this dynamic programming algorithm can go for multiple stages without exponential explosion of your search algorithm. So that's an efficient way of doing this. And tonight, I think the material will be fairly interesting. I don't know if I can put that on the screen. Just want to make sure I have these on desktop PC. Okay, so we are going to talk about so-called optimizing submodular functions. And this, of course, is considered as some kind of a nice property of optimization problem over discrete set. And it's close to what we like for continuous objective function. If we want to minimize our objective function, we would like to see the objective function as what? A convex function. So that, for instance, when you follow gradient descent, you want to make sure that when you get into a stationary point, that's actually the global optimal solution. And in this case, we are talking about something nice in discrete optimization problem, where basically submodularity takes the role of reducing the required computational load in doing the optimization. However, it's still considered a difficult problem, even though some objective function satisfying this so-called submodular property will behave very nice, and still we need to take some issue into account. How can we construct an efficient algorithm in that regard? So this is just an introduction level to this so-called submodular function minimization problem. Of course, if you want to dig more, I think under external link on Blackboard, I have some actually like a manuscript talking about discrete combinatorial optimization. And also I have another reference textbook on your library reserve desk that you can learn a little bit better about how this technique can be applied to real engineering problems. So what I'm going to do is to maybe give a formal definition and then talk a little bit about why this problem is why this is interesting, what are the engineering applications in this combinatorial optimization context. And also I will try to mention a little bit about the history, why people pay attention to some discrete submodular function like this, and what are the early development. And also I will try to mention some reason, well, maybe not so reason, but at least in the late 90s, some development on how this affect theoretical computer science in terms of finding low complexity algorithm for some close to NP-hard problem, and also what are the approximate solutions that can guarantee you with performance close to the optimal one. And we are going to basically conclude that this is a very interesting application domain, especially for some of you who are doing a lot of optimization related to discrete set. So first, let me talk about the submodular function. What is a submodular function? Well, first, still, we talk about discrete set, right? So discrete set in this case is this set E, and then the power set means what? The collection of all the subsets, which means if the original discrete set E contains, let's say, n elements, then the number of subsets will be what? 2 to the power of n. And that's why I have this notation on the collection of all the subsets. And in general, if you say I want to find the minimum or maximum among these 2 to the power of n candidates, then without doing exhaustive enumeration, it's very difficult to make sure that I got the optimal one, okay? So this function, of course, just map all the subset of this discrete set E to some real value. And if we don't specify any property on that mapping, then of course there's no way we can find the global optimal solution without doing exhaustive search. So we have to say what are the required property that we can reduce our search effort. So submodular basically is mainly about how the subset of this power set of the basic set E behave. Okay, so here's just the diagram on the whole set E and the subset of E given by A and B. Okay, so A and B, they have some overlap in this area, so that, for instance, we can see this is A and B, right? And then this is A, O, B, and this area is A and B. So we can evaluate this set or this set. This part is A and B. This is A and B, and this is A, O, B. And of course, we can evaluate the function value for A and B individually. And what I'm trying to say is, if you take the sum of the individual value A and B, and then you compare with what? The intersection and the union of A and B, this part will have smaller value than this. And if this is true for any subset A and B of this of this whole set E, for any subset A and B, if this is true, then we say this function f is submodular. Okay, so what's the implication of this? Of course, this is some property of the function. But why this is something interesting? Well, if you think about, there's an equivalent argument on this, saying that, for instance, if this R contains S, meaning that, for instance, S is the smallest subset of E and R is a bigger one. And E, of course, is some element of this set E. And this is not in S, not in R. Okay? So what we are trying to say is that if you see, I already have a function value S, right? And then if I include another new element in S, suppose I should gain something, right? And this gain, if I have S and I include a new element, the gain is greater than or equal to I have a bigger set and I include a new element. But what does that mean?
Contribution to a smaller subset has more importance than contributing to a bigger set.
Okay. I think this is first investigated by some economy theorists. They say, for instance, the value of some new item, if you already possess more stuff, then the additional value you gain something will be diminishing somehow. Meaning that if I'm very rich, and then you give me some money, the value will be not as large as I'm very poor, and then you give me some money. So, I mean, as an analogy, it's like something like that. And why this is interesting in engineering applications? For instance, if you think about the information that you collect by using different sensors, maybe sensing the same thing, but those sensors are complementary to each other. Then what I'm saying is, if you use the first sensor, sensor 1 collects some information, and then sensor 2, you can gain some additional information by sensing, even though you cover the same scene, then you have some additional information you gain. And then, for instance, on top of that, you have a sensor 3 that can gain another extra information. And the information aggregation actually satisfies this kind of property, saying that the marginal gain will be diminishing, meaning that if I already have sensor 1, 2, and then I add 3, the gain from sensor 3 will be no greater than I only have one sensor 1, and then I want to include sensor 3. To make it simple, this type of function in general is popular when you try to have some kind of information gain, or maybe something that can be converted into some kind of monetary measure where the aggregation takes some role in terms of determining the value of selecting a new element to the existing set. Okay, so with that being said, then that means in real life, we do encounter some submodular functions, and that we can actually determine the marginal value of a new element E to the existing set S, this marginal value is no less than the marginal value of E to a bigger set, meaning that if your original set is small, then the gain will be larger. As you include more and more elements, the marginal gain will become smaller compared with the small set. So that's basically the definition of submodular function. And let's say if we have the number of different colors in this set where you have those nodes A, B, C, D, E, F, G until K. And the number of different colors, if I count correctly, include 1, 2, 3, 4, and 5. So F of this equals to 5. Okay? And does that satisfy the submodular property on this one? That you need to use your intuition and some kind of inductive principle. Intuitively, if you already have a bigger set, then the number of colors probably is already large. You add a new one, it has a new color, the chance will be small, right? Compare with you have a smaller set, right? And then you can use induction to show this is really the case. Okay, so if you count the number of different colors on a subset of this E, then what you see is that, for instance, this set already contains 5 different colors, right? And this is a smaller one. It contains only 2 colors, right? Okay, so let's say if you pick any of these guys outside this, then what will happen? If you have a new color to this, then you have 3, right? But if you already have 5, you don't gain anything. Okay, so that's basically the implication of this submodular property of this function. Okay, so for instance, let's talk about this element G. If you include that in this big set, you still have 5. If you put that into this, then you have 3. That means the gain in this case is 0. The gain in this case is 1. And of course, for any kind of subset you pick, you should prove that it satisfies this kind of property. This gain cannot be greater than this gain. So basically, this marginal value of this element G into the bigger set is 0. On the other hand, this is 1, so this has a larger gain. And that's a very appealing example to show that you do have some submodular function in discrete optimization problem. Any questions up to this point? Okay.
Is there a official or formal statement how to define such a submodular instead of just judged by subjective?
This is not subjective at all. If you look at the definition here, it says that for any arbitrary 2 subsets A and B, you have to satisfy this inequality condition. Or equivalently, you can say for any S belonging to this subset R, you have to say the marginal value of arbitrary element E outside this, the marginal value in the bigger set cannot be greater than the marginal value in a smaller set when you add a new element to the smaller set. You always have at least larger, no smaller marginal gain in that case. So that's actually formal mathematical definition for submodular property of a function.
This is not so intuitive, can be recognized for such a problem. We have some real problems.
If you have a real-world problem, you have to either prove that it satisfies this. Like for this example, once you gain your intuition, you can actually prove the number of different colors is a submodular function.
By enumerate all the cases?
No, you prove by picking two arbitrary subsets.
I don't know. Right now I pick this group and that group, it satisfies the condition.
Yeah.
What if there is just one special case that doesn't satisfy?
Well, you probably shouldn't. In real world, you cannot really enumerate all this. You need to mathematically prove that. Prove this? Any suggestion?
First of all, I think we should first of all properly define our function.
Yeah.
That's the first problem.
Yeah, the definition I think is clear, right, for the submodular function.
Yeah, but for example, in this case, you have taken the image of a subset is the number of colors, but it depends on the problem how you define your function, submodular.
Well, this function is defined by just the number of different colors.
But you may choose, depending on the problem, you may choose some other submodular function.
Yeah, of course. This is just one particular example saying that this is actually a submodular function over this discrete set.
I think that we need to prove it analytically for all arbitrary. We need to pick up any arbitrary subset and we need to prove it.
Yes. Yeah, for a number of different colors. In fact, you can do that for this problem. And that's why here's just demonstration. In practice, you cannot use this demonstration to say, yes, this is a submodular function. You have to use that as your intuition to really show that's the case. Then we can see this is one example. And we have another example that may not be very obvious, but you still need to think a little bit about. This is a graphical model. In fact, you can say it's an undirected graph, where in general, a graphical model contains different nodes, and then between two nodes, there may exist an edge, for instance, in this case, from A to B, from A to D, so on and so forth. So, for instance, in a particular graphical model, you can count the number of connections or the edges. In this case, if I count, this is already, I think, 2, 4, 6, 8, 10, 11. So counting the whole graph, I have what number of edges for all these nodes equals to 11. Right? Okay. And for instance, this function, f, just counting the number of edges for the undirected graph, is this a submodular function? Yes? No? Why not? Well, if you pick some nodes, then what? Then, of course, outside that, the edge you should not count. You can only count, for instance, let's say I pick A, B, and D. Then I should count what? 2 edges, right? And then if I include K, then what? Then I have 3, right? So the gain of this K is what? It's 1. Okay. However, let's say if I already included A, B, D, and G, okay, and then I include K, the gain will be 2. of course, originally it has more edges, but the gain of including a new element to that is what? It's 2. So what can we say about this? It's not submodular. However, if you think closely, this also has some nice property that you can argue. What?
This contains cycles?
I'm sorry.
Its property is reverse to that.
It's like if you think about the marginal gain, originally submodular property is about what? The marginal gain, if you have a smaller set, cannot be smaller than the bigger set. And now I think it's just the opposite, opposite way. If you have a larger set, then the chance of having more edges will be larger than you have a smaller set by adding a new node to the smaller graph. Then the number of edges a new element can contribute would be smaller. But then this is not really very obvious, but we can think about, for instance, if you look at this A, B, D, K, and E, these 5 elements, you count the number of connections in this case. In fact, you can only see what? 1, 2, and 3, right? So you have 3. And if you look at E and K, these 2 elements, you have 0. Okay? And now, for instance, we look at a new element adding to the bigger set. What will happen? You added actually 3 connections, right? 3 edges to the bigger set. For a smaller one, only E and K, the gain is 2. So what happened here? The marginal value for a bigger set is larger than the marginal value of a smaller set. Okay? So it's just the opposite of what we are seeking for, right? But still, it's some very interesting property. If you think about in continuous function, we can have what? Convex and concave function. And now you can see some property analogous to this convex or concave property. So what can you do? If you want to make it a submodular function, originally, it's not a submodular function, right? It's like originally you have a concave function. Can you make the optimization problem a convex optimization problem? Well, of course, you just change your objective function. You'll say, well, for concave function, you need to find the maximum. For convex function, you need to find the minimum, right? So you just change that. For instance, in this particular example, what do I need to do? Just count the negative value of the negative number of edges in this graphical model. Then what? We have this kind of marginal value of a smaller set. Adding a new element to a smaller set, the marginal value will be no smaller than adding a new element to a larger set. Okay, makes sense? Okay, so if you understand about like the submodular function also can have what? Some property similar to what we talk about the convex function. We say if you have a linear combination, or in fact a fan transform of 2 convex functions, still you have a convex function, right? Okay, so now let's see. If you think about the number of colors minus the number of edges for a graphical model, is this still a submodular function?
I think so, because minus
Yeah, because each individual function is submodular. And then you take the sum of that, it is still submodular. How do you prove that? I'm sorry? Mathematically, I mean, high-level idea, not that rigorous, intuitively.
The sum of two submodular functions is submodular.
Yeah. How do you prove that? How do you convince yourself that it is true?
It is because we know that if we add one extra, for example, in case of number of edges, when we include one extra, the number of edges.
Okay.
The negative of the number of
well,
edges.
Because whenever you prove this on the individual function, you want to show what? For any bigger set, adding a new element, the marginal gain cannot be greater than adding a new element to a smaller set. And then this happens for both cases. And then you sum them together. Of course, the marginal gain is some quantity you can compute that adding this together, you cannot really. Yeah, you cannot gain bigger from the larger set, right? So basically, that's intuitively very appealing if you don't want to go through rigorous proof. This should be true for some function like counting the number of edges in the minor sign or counting the number of colors for a graph. And of course, you can see that for some other relevant applications where it may relate to so-called graph cut, meaning what? In general, if you have some kind of network flow problem, then you need to know, for instance, at any particular time, you cut the network from one piece to two different pieces, and then you have a cut. And this cut will basically measure what? Like, for instance, how much the flow going from one end to the other. And then you try to maximize the flow by, for instance, finding the minimum cut of a particular network topology. And this kind of optimization sees in many engineering applications. And in fact, if you think about a graph that previously we only talked about what? Undirected graph. You have a bunch of nodes, and then you just build edges among those nodes. And now you have so-called directed graph. That means what? You need the edge has a direction. For instance, from A to B, the edge is different from another edge from B to A. So in that case, you can think about a directed graph include not only a collection of the node, but also the direction is a pair of nodes, including what? Something like you need to have the source and destination. And for instance, if you think about this as source and that's destination, and then A is basically some subset of the whole set of the vertices not in this S and T. And then what you want to see is basically the number of arcs leaving node set A and S. Okay. So if you think about S is somewhere, for instance, you transmit your data packet through the network, okay? And then this A could be some intermediate routers that you try to think which could be your potential relay of your data packet. Then graph cut is mainly about, for instance, how to count the number of arcs leaving the node set on a direct cut of the directed graph. Okay, so does that satisfy this submodular property? Well, I guess you need to think about these arrows are what? These red are what? Basically are arcs leaving A, right? And this is like you can say a cut of the graph by this A, okay? And then this would be another cut you call B. These arrows counting like these arcs leaving from the set B, okay? And then what? These are leaving from what? A and B. And all these arrows are leaving from either A or B. So this is the union, and this middle part is the intersection. Okay, so now we are counting what? This part is counting the arcs leaving A plus leaving B. And if there's something in between, then what?
We are now counting on the right side.
Then basically this part, do you count somewhere in between?
Yes.
You counted twice, right? Somewhere in between should be counted twice. And for this, you count everything, right? A and B. You count outside, you count inside. And then what?
The black one is not counted, are not counted.
The black ones are what? For the whole thing. In this case, do you count? You do, right? And in this case, do you count? If you consider A and B, you have all these arrows leaving, right? If you have A and B, you have these two arrows. If you consider A or B, you have these four arrows, right? And also, but these will be counted in here, right? But these black ones will not be counted in all of this, right? It will be counted here. This is leaving B, but directly going into A. And this is leaving A, directly going into B. So what can we say? In fact, all these arrows here, you can see that it only counts all these arrows like what it is supposed to be counted. But these black ones will not be counted. So what? So this property will be true for what? For any two arbitrary subset of the whole set. Which means what? Counting the number of arcs leaving the node set A as a particular cut of the graph, this function will be what? Submodular function. Is that clear? Okay, so there are different ways to define submodular functions. Some are obvious, some may not be so obvious. Now let's look at another engineering example where it may not be so obvious what the objective function could be defined that satisfy this submodular property. If you think about an engineering problem of making benefit and risk trade-off, you can say something like these circles are maybe, you can say maybe some sensors you want to deploy to the field. And this could be some kind of maybe data collection mechanism communicating to some sensors, for instance. And of course, if you think about there are different ways to count the risk and the benefit of collecting the information. And sometimes you can say the effort you commit in terms of sensing or data collection by consuming energy versus the information that you gain from the data you collected in the sensor nodes. And you can say, well, I have the overall cost, which is a function of this R, and that's a subset of these, basically this whole set. And that includes some benefit term depending on, for instance, this node, this I in this particular set, and also the risk of exposing this to some collecting node. So these two terms are conflicting to each other. A and B are some constants converting between the risk and the benefit. So one part is positive, the other part is negative, and then you can think about this could be a function defined in such a way. And what can we say if you have a smaller set within this R? Of course, we need to compute what? The marginal risk and the marginal benefit by what? Including a new set I, let's say maybe from here. This is including this to the bigger set versus to the smaller set versus the net cost. Okay, and in fact, if this curve go like this, that means what? Means the whole set, if you interpolate this gain, this is like the marginal benefit from a smaller one, this is the marginal benefit from a larger one. If you always have marginal gain from smaller one is bigger, from larger one is smaller by increasing new set from a new set. For any ordered sequence from the smaller one to the larger one, you can have a curve like this. That means what? This curve will always curve what? In this shape, which is concave, right? Means if it curved like this, means smaller gain in a later stage. Whenever you increase the size of the set, then you have a smaller gain. That means here you have larger increment, then later you have smaller one. And what kind of function can give you a property like this? This is some kind of function like concave. And in economy theory, a lot of people assume that utility function is somehow concave for mathematical convenience. And some people argue that the marginal utility usually will be diminishing if there's a possible saturation at the very end. That's the case. So what I'm trying to say is, in real life, we don't know whether the benefit risk trade-off, this function is actually a submodular function or not. But for mathematical convenience, a lot of people make such assumption to reflect the marginal diminishing effect of adding a new element to the existing set. The marginal gain will be diminishing. Okay. So now we can think about how to optimize the submodular function. For instance, you have a big set E, And then you know the function defined on all the subsets of E satisfies submodular property. How do you find the minimum? How do you find the minimum? Well, I think one thing you can say for sure is still you can exhaustively search all the possible subsets, and then you will know. But is there any way you can avoid doing exhaustive search? Is there any method that's more efficient by taking the advantage of this submodular property of the objective function? Well, in this example, let's say we want to find the minimum ST cat. What does that mean? Well, for instance, here's S, here's T, and then this is a directed graph. You can say you can always transmit something from S to T through intermediate nodes. Okay, you can go like from here to here to here to here to here and then to T. Okay, based on this arrow direction. And a cat means what? Remember, you collect a subset of these nodes, and then what? Count what? Count number of arcs, right? Leaving this set. Remember? No? I think we have this that we talked before. A cut means what? You count these arrows leaving this set. Okay? And how to interpret that? These are what? Possible directions if you want to shape an item from S to some destination T. These are possible routes you got to bypass, right? Okay, so if you look at here, this is one example that, for instance, you circle these, then the cut will occur where? Will occur this, right? And then what? This, leaving, and then this, and this. Do I count this? That's entering into this circle. I should not. Does that make sense? I think so, because when I count this, that means, for instance, if I want to shape anything from S to T, it got to pass this edge, right? Once it enters into this node, it doesn't have to get into this again, right? So it can go directly to here. So this doesn't really matter, but this does matter, because if you enter here, then what? You can only leave through this arrow or this arrow. Same thing for this node. It can only go like this, enter to that node. So for instance, the cardinality of this cut is what? on this card is 1, 2, 3, and 4, right? And for instance, if I want to find the minimum cut, which means what? Somehow I want to make a cut that has what? The minimum number of edges leaving this set, okay? How do I achieve that? Well, I don't want to do exhaustive search, but other than that, there's no obvious way of doing the minimum graph cut. Than this. Even for this small scale problem, can you easily identify what would be the minimum cut for this graph? I'm sorry?
By enumeration, the result is 3. Either just cut S or cut T.
You cut at S or cut at T, you get 3, right? Can you get 2?
No. You can get 2.
You can get 2? How? If you don't want to include S, you probably can. If you say, I just pick one element that has only 2 outgoing edges, then but that's not a legitimate cut. Basically, the cut means something like if you think these are all the possible transportation roads, then where would be the bottleneck, for instance? That's one possible interpretation on the minimum cut. And yeah, more complicated network, it's hard to really find the minimum. And another example of the optimization problem people may spend a lot of time working on is to find the minimum net value. Oh, in this simplified case, the minimum color edge, this colors minus edges on this node set. Okay, so in that case, you can say I want to have as many edges as possible, and hopefully they have identical colors. Okay, and in this particular case, I have 2 different colors, right? And then how many edges do I have? 5. So it's 2 minus 5. Can I get a bigger value than this?
Yes.
How?
Let's include the yellow one.
You want to include this?
Yes.
Then you add what, one more color, right?
Yeah, but 2 more edges.
But 2 more edges. Okay, good intuition. And can you beat that?
1 more green.
This one?
Yes.
Then what?
Edges, 1 more edge, but no more color.
Okay, so you have this whole thing. You have what? 1 more edge, but still 3 different colors. Do you want to add this?
No, that doesn't change.
That doesn't change anything. Okay. So basically, you have some intuition in small scale problem. You can probably do that. But what about the problem is of bigger size? For instance, you may say, if you have some kind of customer support, or maybe collecting sensory data among these sensory nodes, and in general, how to find the minimum net cost or maximum net profit of the customer set or maybe you can say try to find the best way to clustering your sensor network with a leader head and sensor nodes, then this type of problem can be cast into discrete optimization problem, provided you have a given sensing configuration or customer requirement. Then you have a legitimate discrete optimization problem, which you can take the advantage of optimizing a sub-modular function. So now, of course, a critical question to ask is, how do I really optimize a sub-modular function, right? Now, we just talked about, yeah, that's a very nice mathematical property. And occasionally, we can really verify that in real engineering problem, we can encounter sub-modular function. And how can we really optimize? And in fact, I will first introduce a very important algorithm, which I think is very obvious because it's called the greedy algorithm. And I think later, maybe if time allows, I will maybe even spend one lecture talking about greedy algorithm in different optimization contexts, how that can help in terms of solving the problem efficiently, or maybe occasionally finding the suboptimal solution very efficiently with guaranteed performance. So a greedy algorithm basically does what? You choose one element that gives you what? The best marginal gain. And then what? And then once you select, you don't change your decision. What? Then you look for what? The second element that gives you what? The largest additional gain to your objective function. And then what? You keep doing that until you don't gain anything. Then basically you say, well, now that's my solution. Make sense? And that's not exhaustive search on all the subsets, right? Okay, so in this case, for instance, if you think about, this is a graph where you have 5 nodes and 5 edges. And then, for instance, if you say, what node should I pick? And you go first, compare which one gives you the best benefit. Okay, so for instance, if you think about this guy has 4 edges, that has the largest reward, then A is the best I should pick, then I just pick A. Okay? And then what? After I picked A, I look into additional gain I can have. Then basically, I can choose B or D. Well, but B basically has 2, right? Well, the additional edge is here. Okay, D is the same thing. And C, I don't have anything. E, I don't. So let's say I pick that. And then once I already have this, then basically adding new will now create more edges. For instance, then I will stop. And that's basically how I first compare this and pick one, and then I see what would be the additional gain. I pick B, and these are diminishing, then I just ignore that, and then I say I pick B. Okay, and once I have this, A and B, then adding new nodes will not create new edges to my existing part. Then I will say stop there. So you may ask, how well would this algorithm work on submodular function? Well, this algorithm is simple, right? But the performance is very difficult to quantify because what? because we didn't really exhaustively search all the alternatives. On the other hand, there's a hope that this greedy algorithm should work close to the optimal solution in a sense that the function has some kind of nice property called what? Diminishing gain, meaning that in general, if you have larger set, starting from a larger set, the gain is minimal, right? Than from a smaller one. That means from the smaller step, you want to find the marginal gain. In effect, it wouldn't be as worse if you try to exhaustively search on all the possible combinations. So mathematically, you can say greedy algorithm is at least 63% as good as the optimal one. On submodular function. Okay? So that's the nice thing. But of course, there's still some price associated with this. In real engineering applications, you may say this only works for unit cost case. If this doesn't scale very good, meaning that it can also be very slow. Of course, compared with exhaustively search on all the possible subsets, it's efficient. However, the complexity depends on like how much budget you want to allocate in the sensing effort and how many vertices you have. And for large-scale optimization problem, this may not be acceptable. So in real life, we may say we want to have some practical algorithm that's efficient and with guaranteed performance. So we will have a short break, and after that, I'm going to talk a little bit about something more abstract, but I will try to minimize the mathematical description and try to use engineering intuition to explain basically in order to find the efficient algorithm in optimizing submodular function, what you need to do and what are the mathematical theories behind it, what are the recent development, and how in practice you can choose efficient algorithms based on the existing development. So let's take a short break. So do you guys feel comfortable about this part at this point? It's okay. I'm sorry? Submodularity? Yeah. Okay, good.
We are still not very sure about this. About these two questions. This one,
Okay.
The yellow is the distributed sensor, right? Center. Distributed center?
Well, you can say it's some kind of, you can think about if it's customer support, you can say I want to put a customer support center location. If you think about sensor network, this is something like the
hub.
Yeah, like the hub, like the leading node of the sensor,
okay,
of the like the data collection node,
okay,
that can access to some neighborhood.
And the blue?
These are customers or sensing nodes.
Okay. Then what is the risk?
The benefit and risk, okay.
Benefit, what is benefit? The closer, the higher benefit?
Well, you depending on, for instance, in the sensor network context, of course, the closer the better, because you spend less energy to collect, to communicate to those sensing nodes.
Okay.
And
so what is alpha? What is beta? What is A and what is?
These are constants. These are just some engineering trade-off between something like the energy you spend to collect the data and then the benefit in terms of the, for instance, information gain from your sensory data.
Then what is beta? Beta means?
These are related factors of a new sensing node. For instance, you can say it's like when you include a particular node I, then you have some benefit term associated with beta I. Then you have some risk term associated with sigma I. These are conflicting to each other in general.
Okay.
In general, you can say maybe some customer may be helpful in some aspect, but when you try to collect the information, you pay some price. Okay. And for sensor, I think it's very similar to, for instance, if you awake this sensor to collect data, then you spend some energy. Like there's a trade-off between, for instance, this data is important, you put some value, and then it costs you some energy to get that data. Then you have some balance between these two terms. Of course, you may say, well, in real life, this doesn't satisfy this nice property. That's a problem. But in economy theory, people always assume some nice thing will happen, so that will simplify the mathematical optimization problem much significantly.
And this one we don't know too. At the beginning, they are all green.
I'm sorry?
At the beginning.
At the beginning, yeah. Of course, you want to pick a subset, for instance, so that it contains, it has the maximum number of connections per edge.
For example, at first we pick up what is the start point? The start point A.
Well,
only pick A.
Well, you pick any one.
Okay.
But which one has the maximum number of edges?
Yeah, A.
So you pick that.
Okay.
Okay.
A is edges is 4. FA is 4.
Yeah. And then what? And then
change
you have the rest part, right? Which one gives you the largest marginal gain?
Yeah, pick B.
B or D doesn't really matter. Once you pick that, then you will stop, right?
Yes. Yes. Then we stop here.
Okay, and that's greedy.
Okay.
So D is also okay for the, for example, A and D.
Yeah, you can also you can also pick that. Yeah.
This is just like a gradient thing. While we are here, we graded it.
Well, this is greedy.
A little. I mean the.
Meaning that once you make the decision to pick someone, you cannot change.
Right. This can only go one way.
Yeah. And the initial decision, if it's very bad, then later there's no turning back. And that's why, in order for this initial decision to be reasonably good, we have to ask the function to satisfy so-called submodular property.
Actually, I'm very interested in the percentage.
That's 1 over E, and E is a natural logarithm.
Why at least? Meaning this is
That's a worst case theoretical bound. Yeah, like a greedy can perform at least.
Most of cases.
Well, no, it's not most of the cases. It's like in all cases, the greedy solution will have the function value at least 60% to the optimal solution that you can ask for.
This is optimistic.
I'm sorry, this is
Optimistic. Intuitively, and maybe there are some worst cases.
well, this includes the worst case scenario, meaning that in the worst case, the greedy solution is at least 60% close to the optimal one. Without submodular property, there's no guarantee. You can say, here's the optimal solution. Any other, what you call suboptimal solution procedure can be arbitrarily worse. Well, I mean, in Dr. Lee's opinion, anything not to that close to that optimal is not really acceptable. But in real life, we don't know. We have different ways to justify why something like on average you're doing good. But in the worst case, you can be arbitrarily worse. Or if you want, you can say, well, in the worst case, I'm still at least 60% good. On the other hand, some may say, well, you are very conservative. Because most of the cases, maybe you already found the optimal solution, but you don't know. All right, so now I think we will get into something a little bit abstract, but bear with me, it's not that incomprehensible. So on the left-hand side, you are looking at optimization problem. You can say this is some very interesting geometry type of problem. If you think about this is some polyhedron area, okay? And then you want to find some value, some point x star belongs to this P, such that, for instance, this Cx star is greater than or equal to Cx for every x belongs to this P. Meaning that, for instance, you can say, I want to find this solution, okay? And this is what? Nothing but like a linear program. Okay, you want to find this. Okay, on this side, it's also another interesting geometry problem. You say, well, I have the same polyhedron, and then I have this initial point, x0, and I know this initial point, I know this polyhedron, and I want to make a decision on whether this belongs to P or not. If this is inside this or outside, or equivalently, if you say it's outside, which means what? You can separate between x0 and the polyhedron. You want to say a point belongs to this set or not belong to this set. Can you find an efficient algorithm to test if a particular point is inside the polyhedron or not?
We can, from the point, we can draw tangents. We can just try to join the point to each of those extreme points. And if it becomes a tangent to,
well, first, let me ask you this. Which problem you think is harder? This one or this one?
Checking whether the point is inside?
Yeah. Or separation problem or optimization problem? Which one is harder?
I think optimization.
Optimization is harder.
Yeah.
Why? I think your intuition is correct. This one, what you need is to essentially going over these vertices, right? Like when we talked about simplex, idea of simplex. And this one, it's just like a verification of a bunch of inequality constraints. Do you agree? Because this is a polyhedron. If you want to know whether it's inside or not, you're trying to verify what? A bunch of inequality constraints. It's just constraint verification type of problem. And this, of course, I believe you you can write a program that works efficiently for this, for separation problem. Okay, but now comes to a very interesting mathematical claim. Of course, by a group of people, and Lewis and Schriver, these are very important mathematicians, contributed to the discrete combinatorial problem significantly in the last century. So what they found is that the optimization problem for some polyhedron can be solved in polynomial time if and only if the separation problem can be solved in polynomial time. What does that mean? Yes?
If optimization problem can be solved in polynomial time, automatically know the same thing holds true for separation and
Yeah.
vice versa.
But intuitively, we just said this looks easier, right? And this looks harder. But mathematically, they are equivalent, meaning that there's a hope what? The optimization problem should have polynomial solution. Okay. So if you think about, on this side, you have the optimization problem where you can also go for what? Some kind of greedy solution. If you think about this along two directions, E1 and E2, and then, for instance, if the cost for E1 is greater than or equal to E2, then you first get to E1 and then see if there's the largest marginal gain along that to get to the best solution. And of course, in this part, we want to say if there's a legitimate test on whether this point is inside the polyhedron, then this problem is in fact equivalent to minimizing a submodular function. Okay, and based on that, what can we say? Minimizing submodular function has its own right in mathematical optimization because what? People have strong belief that there should be some efficient algorithm you can solve for that problem. Okay. So now let's formalize this discussion by saying that if the optimization problem and the separation problem are polynomially equivalent, then we can see that the optimization problem for this polyhedron should have a strongly polynomial combinatorial algorithm. If there is a strongly polynomial combinatorial algorithm that can solve the separation problem. Okay, and the separation problem looks easy to us, so mathematically, people conjecture that there should be some strongly polynomial algorithm for submodular function minimization. Does that make sense? Well, this is the history of mathematical theory development along this submodular function minimization. If you retroduce to submodular function on Metroid, and in fact, the early work is even before what? The invention of linear programming. Okay, that means submodular functions and optimization are actually important in a lot of engineering applications. People already spend time looking into how it works. And of course, one connection to greedy algorithm, which maximizes linear functions over polymetroids, was discovered in 1970s by Edmonds. And then later, I think this groundbreaking paper talked about polynomial solvability of submodular function minimization via so-called ellipsoid algorithm. I think if you recall that when we talked about solving linear program via simplex, the complexity can be exponential in the worst case. And at that time, like a group of Russian mathematicians invented this ellipsoid method, which guarantees to have polynomial complexity. So this ellipsoid algorithm was considered very effective. However, in engineering applications, it doesn't run as efficient as simplex in most cases. So it's kind of interesting. But later, of course, entire point method becomes the dominant technique that has theoretical proof of polynomial complexity and also scales very well for large-scale linear program. Anyway, so when you look at the combinatorial optimization problem, you always think about like what are the existing algorithms that can provide you efficient solution. In this case, up to 1980s, people already recognize that the greedy method can have at least 60% close to the optimal solution in the worst case. And then, of course, much effort has been made toward finding strongly polynomial algorithm for specific submodular function minimization problem. And in like very recent years, strongly polynomial combinatorial algorithms have been developed by, of course, a group of people, especially I think Shriver, who actually wrote a multi-volume textbooks on standard combinatorial optimization and optimization over metroids. Okay, so I think some of you may not like this, and especially when it comes to new terms and definitions. And Lippy has some math background, so I mean, I try to make an analogy between the gap between students in math major and students in engineering major. Usually, students studying math, they like to see rigorous invasion on, for instance, what is the definition of something, right? And can you prove that this algorithm works? Can you prove that it converges? Can you prove how fast it will converge, right? Things like that. As an engineer, usually they ask, if this theorem is true, how do I gain? What can I learn? Can I write an efficient program to solve some real problem or not? And that's why, for instance, it's hard to make some compromise between rigorous mathematical formalism of optimization and a good connection to real engineering problem. So here's the mathematical part of the supporting material to say that minimizing submodular function is possible by finding some good efficient algorithm. And this also works for so-called metroid. How many of you heard about this, except Lippy, about the metroid?
Not even Lippy.
Okay.
I didn't hear it about metroid.
Okay, this is basically a way of defining some abstraction of like some kind of graphical model, which is something like you think about discrete set and then some operation, some function on top of that. And then this is basically first you need to have this E, the finite set, right? And then you can talk about the subset, and then you can talk about subset selection, optimization on this. And then this I basically is a collection of the subset of E. And some people call that the independent set. And in general, this metroid should satisfy some mathematical conditions. that may not be as restrictive as submodular, but still it's something very interesting to think about. You need to have the empty set, and then the subset of independent sets are still independent. And all maximal independent subsets are in this finite set. Of course, you can define the rank of these subsets A, or you can define this function, which essentially is about, because it's counting the size, you can verify it's like counting the number of different colors of the nodes. Very similar to that, you can say it's a submodular function on E. Okay? So basically, a matroid, you can say it's a way to what? Abstract some submodular function optimization problem to a more general context in the discrete setting. Okay, so we cannot talk about anything without examples, I guess. So here are the matroid examples. If you consider like the forest matroid of a graph, okay? So a graph in this context is a collection of vertices and edges. So you have a set of vertices and set of edges of this graph G. And then matroid is basically about what? Subset of these E edges, where I only care about edge sets with no cycles. Okay, so for instance, here are 3 edges, okay? And I don't have any cycle, right? And this is 2 edges on these 3 nodes. I don't have any cycles. So I can define that. And then I can also calculate the rank on this collection of the subsets. I want to have I. This has the largest cardinality, which is the edge set of a forest. Okay, so basically you can say I want to collect all these edge sets that cover this graph, and then I want to find the largest cardinality on this.
Here we only consider the forest, only the edges in a forest. It means you don't consider those 3 edges into those 2 edges together in one set.
Yeah, I collect this in one set, and they don't have any cycle in all the cases.
Those 5 edges are in one set. I think they are in 2 different sets.
Yeah, they're in 2 different sets.
It means you consider forests. You don't
Yeah.
consider independent forests.
Well, I consider, for instance, this is a tree. That's another tree.
Yes.
A forest means a collection of trees.
So those 5 edges can come together in one subset.
Well, a collection of that could be a subset. So the matroid basically is about the collection of these trees. And in fact, you could also consider cases where you have the edge sets where you don't have any cut sets. Meaning that, for instance, you can separate this part with this part. And of course, in all these cases, once you define the rank function, then you can see that, in fact, all these can be cast into some submodular function. For instance, if you ask the question, can we partition the edges into, at most, K forests? Then this question means what? I have all these edges, right? And then how can I partition them into what? Into forests means what? You cannot have anything that contains cycles, right? Meaning, for instance, if I say this is a particular tree, then what? This would be another particular tree, okay? And then I could have another tree like this, okay? And then another tree like this, for instance. I could have another tree like this, but I cannot have a triangular shape like this. Make sense? And then, for instance, in order to form a partition, how many elements in this case? Like this, if I say this is a legitimate partition, then what's this value, k? Like how many trees do I need to have there for this partition? Have 1, 2,
And then 3. The green one, the two green ends.
and
Yeah, those two green ends.
this tree,
No,
this whole thing.
Yes.
Yeah, this whole thing is tree, but this has a cycle, so it got to be what?
No, not that one. The one with the green ends. Two green.
Well, if you look at this color, this one, this you can say it's the whole thing can be considered a big tree, right? The red.
Yeah.
And then this light green is another tree, okay? On the other hand, this black
Black is
is not, then I need to have another one. So 3 is not right. I need 4 in this particular case.
those first four red edges will form one correct.
Well, each color you can say represent a tree,
Yeah.
but except this black,
Yeah.
it's not.
We need 4.
Yeah, so in this case, we probably need 4. If you can make it 3, then you need to change your coloring scheme. I don't know if you can make it 3. That's an interesting combinatorial problem. But in fact, this is actually a submodular function if you think carefully. Maybe you think? I think the major challenge comes from this part. This is a clique. For this 4-node clique, probably you need 4. Well, this is a very interesting problem, but probably, I mean, if it's just purely for graphical model, it doesn't really matter too much. But in fact, for some students who took information theory and learning with me, probably know a lot about message parsing over graphical models, which require you to basically model the dependency using some kind of graphical model like this. It's including Bayesian network or some other type of formalism for some graphical model. So there are a lot of interesting operations you can apply on Metroid, including intersection, union, and some other operations. There's also another interesting case of submodular function minimization problem. You try to find the maximum matching in a bipartite graph. So how many of you heard about bipartite graph? You heard about that? Which means what? You can say the graph contains 2 groups of nodes. You can cut them into half. Those edges, if you cut, you put them into 2 sets. So it's a bipartition of the nodes. Okay? And why that's interesting? For instance, a lot of optimization problem can be modeled as, for instance, assigned tasks. Like you have, for instance, 5 sensors collecting data, tracking maybe 10 objects. how are you going to assign sensor to object? That's assignment problem, right? You can think about I have maybe 13 students, and then I have maybe 20 tasks. And how should I assign tasks to students in order to optimize some overall objective function by completing all different tasks with different values upon completion of each task? Then those things are considered as the matching problem. And maximum matching in this bipartite graph means something like you can create the best correspondence from the source node to the destination node so that the overall cost can be maximized or minimized depending on what objective function you use. So this is also an interesting problem. In general, a lot of problems can be written in terms of submodular function minimization, where you have one part on this side, you can say it's like doing optimization problem. On the other side, you can say it's like finding the best separation, like what we see in that contention between some problem people believe there should exist strongly polynomial algorithm to solve the problem optimally. On the other hand, the other part, we don't know. So if people work on this problem and know that it has integral optimal solutions, meaning that if this thing has solutions relaxed from the integer constraint to the whole ranging from 0 to 1, and the optimal solution still is integer, then basically this problem can be solved efficiently. And that's why basically this D model is important in a sense that characterize what kind of efficient algorithm there's a hope we may look for so that we can solve the problem. And submodular function minimization is important. So let me make some intuition on discrete optimization problem. In general, you may say if you have a real problem, you can either prove, okay, this problem is somehow equivalent to a NP-hard problem. That means this problem, the formulation, means it's difficult, right? And then there's no hope you can find efficient algorithms that solve the problem optimally. Or you can say this problem is somehow polynomially equivalent to submodular function minimization problem. Then what? You have a strong hope that you can find a polynomial algorithm to solve this discrete optimization problem efficiently within polynomial time. So if you have a problem somewhere in between, what do? You can always borrow the idea from this branch and bound and the duality theory that we talked about before. You can always try to lower bound your problem and then what? Provide some way to certify, okay, so now I know that my solution is optimal one by eliminating all the infeasible branches from the lower bound. And of course, that's like in real world, that's how people try to attack the most difficult problem in discrete optimization. And this is basically the real formalism of so-called solving submodular function minimization problem in polynomial time proposed by Shidriver. And that's really something very nice because it uses all the essential ingredients of optimization technique that can actually address this problem in a very nice way. First, it has some kind of analogy that you have a hard problem, and then you try to at least cut the piece so that you say certain part could be equivalent to an easier one so that we can solve that. And then decompose a difficult problem into some tractable, relatively easier ones is one important technique you should learn in engineering optimization. Other than that, of course, need to have essential knowledge on how to separate between problem, which is like NP hard, and some problem which is a polynomial, which is solvable in polynomial time. And of course, by looking into this, we try to avoid just say propose a greedy algorithm that is 63% as good to the optimal one. We try to say, well, there's a hope we can propose a polynomial algorithm that can find the optimal solution. And this is basically the whole picture of this Schrigiver's algorithm for minimizing submodular function. And what does it do? Intuitively, if you don't go for greedy, what do you do? You need to have some kind of analogy, like what you learned from branch and bound, right? If you greedy means what? You make a decision, there's no change. If you want to change, then what? You need to have some backup. Do you agree? If I say I want to pick the best student in my class, I pick one student I cannot change. But if I say later I may change, what should I do? I need to have some kind of ranking mechanism. At least I know the candidates. Later, how should I change based on what criterion I should change? And that's the same thing when you have a bunch of sets in the feasible set. On the other hand, if you have too many candidates, then you face the combinatorial explosion of your search space. That means your algorithm is not efficient. On the other hand, you need to control how you branch in different directions, not like always go for greedy. You can have the backup plan. And of course, first thing is to prove there's a way to always control your feasible set that with limited complexity. And that Schrigiver's work did that by showing that, in fact, it is possible, where he can find the best subset that has all the negative components and no positive components on X, where this function basically can be lower bounded by that. And once he has this, then the next step is to decompose that into some ordered set in order to basically solve the larger problem by smaller ones. And then those smaller ones, you can say it's like each one you can think about using some kind of greedy algorithm you solve. And then you compare, okay? And of course, mathematically, you can say this enumeration should be controlled without without any bound. You have to enumerate all the possibilities. And that's basically how you try to solve this by verifying the optimality condition. Okay, so for example, if you evaluate this set with function of the whole set is minus 71, which provides some legitimate lower bound on the subset. And then let's say if you evaluated 3 guys where you get this, And you say, well, in this case, it's actually a legitimate lower bound. And what do? You change your combination of two branches so that the ordering will give you the best solution to the shifted subset. Meaning what? For instance, if you say I don't want to go for greedy, I have, for instance, let's say at first stage, I have two candidates, and then selecting one will have different marginal ones based on my second decision. So how do you control that this branch will not go like always whenever you maintain two candidates, you have two more candidates to consider in each branching procedure? If you say, I don't want to go for greedy, I want to always keep two candidates in each selection. I select one or the other. And then how should I control this branching? Well, in this case, you always find a lower bound and then try to combine these two decisions based on a weighted sum of the lower ones. And then using that idea, basically, this Shijiwa algorithm works on a general graphical model that accounts for all different nodes where you have positive sign on one end and you have negative sign on the other end, and then you connect these edges where basically you have a path from positive to negative, or you don't. And of course, you can think about a subset that creates some lower bound, you can say lower ideal, in this preference set, where this basically minimizes the subset that you have so far. And without this step, you cannot say, I should not branch further. With that step, you can actually control. And based on the second case, that there is a path from positive to negative, then you have some kind of flow coming into this edge. From that, you need to basically solve another ancillary problem, and solving that requires some iterations in this case. So this part is important because how you enumerate this requires some kind of ordering preference between something like if I have two students as a candidate, and then if I say, how do I pick other two students to make a team? It's very similar to that. And how do I test which two will work together, for instance, maybe providing a better outcome? And in this particular case, if you say I need to exhaustively search all the companions, that's not going to work. What he does is to create some kind of linear combination of the teams so that he can evaluate once and then get to know basically what will be the results for all the combinations of the rotations. Okay, so, well, I guess some of you may already completely lost. Okay. So let's say if you are working on the term project for this course, okay, and then let's say we want to find, for instance, let's say we have one assigned term project. I want to find the best student group who can actually contribute to the best performance to that project. If you want to make a decision, what do you do? I'm sorry? Well, make some suggestions.
Yes, yeah, pick my friends.
You pick your friends, okay. Well, in general, greedy means what? Greedy Well, greedy means something like I let individual student work first, for instance, to see what happens, right? For this project, I say, don't collaborate, each work on this. And then, for instance, let's assume that Lippy got 98, which is top 1. Then, okay, so I say, well, she should be in this group. Okay, and then what's next?
Clone Lippy and add the
Okay. Okay, and then see who can make a difference on top of her work, right? And then let's say the second best is from resting, and then I say, well, we need to pick this, pair them together. Okay, for this team, then what's next? You always try to find any other student who can contribute. If later you say, well, these two probably can do everything they want, then we stop. Okay, but this works when the first choice is correct, and then the second choice always complement to that. Everything works ideally like that. What if the first choice is not the best choice when we want to find the team? There's no turning back, right? Of course, ideally you may say, well, if you do the individual examination, what happens is that, for instance, maybe Lippy ranked number 1 and resting ranked number 2. What should I do? Well, I would say I have 2 candidates, right? And then, of course, it's very convenient to pair them together to see what happens. But in general, sometimes they will pick their best companion somehow. And then, for instance, in that case, the brown team will go, for instance, they can pick their first choice or second choice. Maybe let me use Lippy as an example. Maybe she picked Nan as her first choice, and then she picked maybe, let's say, Saya as her second choice. And then you have 2 groups, right, to evaluate. Of course, you can still apply marginal gain, but the problem is that when you keep doing that, you accumulate a lot of, you are effectively exponentially grows your potential candidate groups. And sometimes maybe Resting also picked Nan as his first choice. Maybe he picked Mr. Liu as his second choice. And then you have all this kind of exponential growth. How do you avoid that intuitively?
Constraints?
Make some what kind of constraint?
You limit who can work with who?
Well, but then you probably will lose some optimality somehow. If you don't evaluate, you don't know.
Constraints only if 2 students pick a common student.
Okay, yeah, of course you can always add some constraint. The problem is that if you make a new constraint, sometimes that it's like I subjectively already have a preference saying that the optimal subset has to be within this. But how do I know that without a formally test?
You optimize the choice. If 2 students pick a student.
Yeah, in this example, there's no way we can really do any optimization, right? Because we don't know if this objective function is submodular or not. Let's assume it is, then the implication is what? You can do something smarter than directly pick 2 groups and then evaluate the outcome. You say, I try to evaluate the effect of the combination of this effort together. And how to do that? It's because the submodular function has some marginal gain property. And Shajiver's idea basically is like, for instance, right now, I already have possible choices like Lippy wants to partner with Nan, and maybe Resting wants to partner with Mr. Liu, and so on and so forth. And then there's a way that I try to envision what happens when these 2 groups act together with some weights. And then based on that outcome, I can basically already tell basically some branch I will not examine, for instance, the possibility that, for instance, resting will pair up with LP somehow. And then because of that, then the complexity will reduce. But of course, it's not so obvious how that happens. And that's why you see a bunch of equations or notations on how to rotate the variable so that the original problem can be decomposed into smaller scale problems somehow. And of course, in this course, you're not supposed to learn all the details on how to invent such an algorithm. But I hope that at least you get some idea how basically a real engineering problem can be addressed by some approaches which produce efficient, close to optimal solution. And in this case, of course, as a mathematician, Shijiva always seeks for the optimal solution. And the solution always has some nice geometry property on how they rotate on these groups, like possible pairings. Without even looking into all these pairings, there's a way to basically map into how they will perform in order to determine what would be the next candidate, whether you want to include in the group or not. So that's basically the idea. If you evaluate all this, that will not be very efficient. But if you know this can map into the next best group, then basically you implicitly already made your decision. And that's like geometrically how the iteration works. And of course, the whole algorithm has a complexity as a polynomial function n to the power of 6, which to my knowledge was considered the best achievement in the combinatorial optimization. Any improvement upon this power would be considered a significant breakthrough in this context.
Each time you make a convex combination of those candidates.
Yeah.
So you need those coefficients.
Well, not just that. On top of that, you have some small, how you decompose the problem depends on the previous stage. So it's like one analogy is like you don't solve the primal problem directly. You first need to convert that into some dual representation. And then from that angle, you can do this combination. And of course, the most important part you may want to learn is that this submodular function minimization is considered a very important optimization technique for combinatorial problems. And in real life, we do utilize this technique to solve some problem. Like even in my own research, I'm working on sensor management problem where we need to allocate sensing resources and assign sensors to track different objects so that certain information gain can be maximized. And by using submodular property of the information gain objective function, we can find some efficient algorithm to solve the problem close to optimal with guaranteed performance, with some guaranteed worst case performance gap between what you have and what the optimal solution you expect to achieve. Of course, that you don't know. And submodular function minimization is in general still NP-hard problem, but efficient suboptimal approaches always exists. Under some generic context, like a graphical representation of the matroid, in fact, to my best knowledge, Shijiva's elegant algorithm, which was considered the breakthrough in terms of finding the polynomial solution to the optimization problem, which is analogy to finding the solution in separation problem to the order of n to the order of n to the power of 6, which is considered the best complexity bound for this type of problem. And that's pretty much what I want to give you at the introduction level of what submodular function optimization is. Any questions? Well, I guess the bottom line is if in your research field you encountered some combinatorial problem, you may need to at least know some existing techniques. Like this problem can be found, that this problem have some nice property that you want to exploit. Do you think the problem can be formulated as dynamic programming? Can it be approximated by dynamic programming formalism? Can it be solved by assuming this objective function has submodular property? Can I apply greedy algorithm to solve that problem? Can I apply some other advanced algorithm that's that has polynomial complexity, which means it's efficient and can scale well to large scale problem? And these are important things maybe you need to know. If you don't encounter such a problem, then of course you will never actually spend time looking into the technical details. But still, other than that, another important thing you may want to know is that in general, people look into optimization problems into different aspects. At the theoretical level, some people prefer to classify the problem into relatively easy ones and relatively difficult ones. Okay? And easy ones means something like I know I can use computational resource to solve even large-scale problem without too much difficulty. For instance, like a linear program or convex optimization. And in discrete case, like dynamic programming or submodular function minimization in some special cases. And some problems, people prove that the problem is as hard as some notoriously hard combinatorial problem. Like for instance, you'll say finding the global optimal solution when you have many peaks and valleys in a bizarre objective function. Or a combinatorial problem where it's equivalent to traveling salesman or some other NP-complete problem. And then those problems, if you immediately recognize as a hard problem, then you will stop seeking efficient algorithm that can give you optimal solution. You can always settle with so-called efficient suboptimal algorithm or efficient non-optimal algorithm, to be more exact. And suboptimal in this context means there's a way you can actually know the performance gap. And in some cases you do, and in other cases you don't, like you run simulated annealing or genetic algorithm, which I think in the new computer assignment, you're going to have some chance to implement or at least partially implement some global optimization techniques. So for that matter, I would say it's a way that you can actually gain some hands-on experience to optimization problem. Once you know like these two groups of thinking, then of course it boils down to like I have some real engineering optimization problem. What should I do, right? You can always make a choice. You can try to simplify your optimization problem by making it easier to handle and try to gain some insights. Or you'll say, I don't want to waste my brain cells, so I just make it as hard as I can. Then in general, it's like NP-complete problem. And by doing that, in general, you don't gain too much insight in what technique you're going to use to solve the problem. So I guess that's what I want to say. And now I hope that I can give each of you some opportunity for you to talk about like, I think last time some of you already talked about like the optimization problems you are going to put in your term project and you want to put some thoughts. And now I think I will leave the atmosphere open so that you can talk about like what problems you are interested, and in general, you really, it's maybe even beyond your own current research, but you want to look into. And of course, in the context of engineering optimization. And also, maybe if you want, you can also add for the rest part of the course, which part you may want to know more, so that if I can, I will try to prepare according to the individual needs. Okay, so maybe let me now to directly pinpoint to some students. Anyone wants to say something? Yes. I thought you.
Sure. I'm still thinking of the airplane and waypoint problem.
Okay.
I still don't know how to do it, other than with like simulated viewing or something. So I'm just letting you know that's where I am.
Okay, you're interested in that problem. Do you know how to write down the objective function you try to minimize?
Kind of. I mean, like if you have a set of paths.
Okay.
I can determine the amount of time that would take.
Okay.
But I'm having a combinatorial problem.
Yeah.
Because not only do you have to distribute these waypoints, but you also have to distribute their order correctly.
The assignment.
Right.
Yeah.
Not just the assignment, but
also the order. Yeah.
Right. So it's a huge number of possibilities.
Yeah.
And it's not something that you can write in a simple objective function form, I don't think.
Yeah.
But given any combination, you can very easily evaluate the cost.
Well, yeah, you can evaluate the cost, but right. The problem is still there's no obvious way to search for efficient method solving that problem, right? Except some like integrality constraint that you can relax, or maybe using branch and bound. Other than that, I
don't see those techniques being applicable.
Okay, well. Okay, so anything else you want to add?
No, I've been here for the last 3 weeks thinking about it, not making any progress.
Okay, yeah, of course that's already proven NP hard problem. So.
But it has to have a solution.
Yeah, of course. I mean, you can find a solution, but the problem is there's no way we can even find some bound on how close you are to the optimal. Right, and that's a problem. And also for some problem, for some, I would say, small scale problem in code, like the example I provided, you can run some standard package to really get to the optimal solution, but it doesn't really scale very well.
But how would you even for a small scale problem, other than the complete enumeration, how would you solve it?
Well, it's based on.
If you didn't use one of the built-in packages, like if you had to write your own.
Yeah.
I don't even know what approach I would use for that.
Well, that I think you need the branch and bound for sure, and also in the branch and bound part, you need a good way to successively relax the integer constraint. Okay, I think we can talk about that even after class. Yes, Libby.
Dr. Chen, actually, I have two projects in mind.
Okay.
For example, one of it is using the non-negative matrix factorization with sparsity constraint.
Oh, sparsity constraint, meaning you.
Talking about sparsity constraint.
Yeah. Okay.
I have a non-negative matrix, and I want to factor.
Usually sparsity is something you can pursue, but it's hard to make it a constraint. but I think I will get into that maybe in the later stage.
And another problem is what you suggested in the last bioinformatics group meeting. You remember when Dr. Duman was presenting and he mentioned about Dr. Lee's paper on
constrained list squares.
And he said you suggested to take it as a class project to how he uses Lagrange multiplier, how he computes
Well, I'm saying that, well, I don't know about what Mr. Duan is doing on that particular context, but what I'm saying is if the original formulation is a constrained list squares, then you should pursue for finding global optimal solution using iterative method through successive Lagrangian relaxation. And that, of course, there's like a standard package for doing that. But then, of course, if you have non-negative constraint, things will be a little bit complicated in that case. But what I'm saying is you can still pursue for sparsity with non-negative constraint. If that's, in that context, if that's the optimization problem you are trying to solve. Okay? Anyone else? I'm sorry?
No progress. We've been working 22 days straight. So.
Okay. But do you think that sitting here, you can actually gain something from this course material?
I've thought about this thing, this user side demand thing with the smart grid.
Okay.
Actually, I'm going to talk to have been talking to somebody over at Tulane, believe it or not. Not an engineering school, but a business school.
Sorry.
And, we're an engineering school.
Right.
And and he has written some papers, but I think that the problem might be more trying to define what you can't do and what you can do with it, because it's so random with the way usage is. And the point is what you were saying. How do you set up the objective function? I mean, it's pretty obvious. Everybody wants to pay the lowest amount of bill and consumption and optimize their usage. But how do you really describe that? And that's the tough part.
Oh, I see. But that doesn't mean you can write down the mathematical optimization problem. That just means you have some vaguely defined objective function. But of course, sometimes you may have to simplify your problem a little bit so that, so that you can gain some insights by solving, even though somehow naive optimization, which by looking at the solution, maybe you can gain some insights into how to make it more realistic in the engineering applications.
If an objective is a target, could you consider that? Is an objective a target of what I'm trying to achieve?
Well, in general, what I'm saying is you need to maybe just have as few decision variables as possible at the very beginning. And then also you try to at least write some simplified objective function based on some empirical model from the decision variable to the objective function you're trying to maximize or minimize. And then, of course, you'll try to see if there's any way to make the feasible set and constraints more or less mathematically tractable. And of course, if you want, you can take a look at the assigned term product, which contains like the image file and also description on how you can basically sketch the image, which is just like a standard grayscale image 256 by 256. And then you sketch that by, let's say, originally you may need about over 65,000 pixel values to record that. And then now, let's say if you only have 10,000 measurements, sketches the image, is there any way you can recover from that? Well, you don't take pixels randomly. What you need to do is to combine some pixel values somehow so that you can actually recover. Meaning that, for instance, let's think about you have, let's say, 65,000 pixel values. You do a random selection of these pixels and then you do a linear combination of those randomly selected pixel values, for instance. And then use that. If there's a hope, you can recover those pixel values. Of course, you'll say, well, that's ill-posed problem. Because let's say you have 65 unknowns. You only have 10,000 equations. How can you solve that? So if you have 65,000 unknowns, you have 10,000 equations. You cannot. What you can do, of course, is to put additional constraints on that. Like, for instance, pursuing for sparsity. And in this case, you can say the intensity change of the pixel value on the image between certain neighborhoods shouldn't be too large. So that maybe you'll say the intensity peaks should be minimized so that the total variation between the reconstructed image and the original one is minimal. And by reading the description, you probably can get a better idea. And then, of course, the problem is, how can you solve that constraint optimization problem? Even I tell you, pursue for sparsity still, we are doing optimization problem with over 60,000 decision variables. If you run any standard package, it won't work. And the question is, how are you going to solve that? And to me, that's a real test. If you can solve that problem, that means maybe for some other engineering optimization problem, you have a way to handle it. And I highly suggest that you download the convex programming package CVX and try to use that package to do your modularized program. If you choose to work on this assigned term project topic. Of course, I may want to create some competition on that one. If you can solve that problem to a certain satisfactory level, you can win some small trophy at the end of this course. Yes, Sam.
The problem that you just mentioned, Dr. Chen, is it possible just to use some pattern recognition techniques, like SVD, for example, to make it simpler?
To make what problem simpler?
The 65,000 decision variables that you sort of reduce the dimensions.
Yeah. Well, in general, I think in your research field, bioinformatics, you also need to consider some kind of sparsity when you have more unknowns, when you have more variables than the unknowns, right? For image, if you know the actual contents, then of course you can make assumptions on that. Because you can do image compression, right? For instance, do you know how this JPEG or other image compression algorithms works? You know? Okay. So basically, what it does is just like partition the image into patches and then do some kind of discrete cosine transform or discrete wavelet transform on the zigzag, and then you do some arithmetic coding, and of course need some knowledge on the information theory part, what's the best, to what extent you can compress. The problem is when you don't know this image, well, what's the contents? How can you compress? You cannot. But still, there's a way you can sketch this image without knowing what would be the actual contents. That's the nice thing about how to really do a sketch of the image. Let's say you know this image is 256 by 256, right? You know it should contain above 65,000 pixel values. But you can only make, let's say, 10,000 measurements. Is it possible to recover that image?
Do you have limitation about how many pixels you can get?
You can always get those pixel values, but what I'm saying is those pixel values, you cannot directly record those pixel values. What you can do is only take maybe 10,000 measurements, which could be any combination of your pixel value if you want to. But the problem is with these 10,000 measurements, how can you recover those 65,000 pixel values? Of course, you need additional assumptions. That's why I said that, for instance, you think certain pixel values are redundant because the gradient should not change too much. that should be true for all different images in order for you to recover. And that's why, even though I have the testing image, which is standard sample image for image from the image processing field, it's a boat, I still provided some other testing images for you to evaluate whether your optimization technique works for some other context. I would say that's a very interesting term project that I would like some of you to work on and also sharpen your optimization scale so that you can handle over 65,000 decision variables in the optimization formulation. So anyone else wants to say anything?
Well, I have a question.
Sure.
For those kind of NP hard problems, if I got a problem, I don't want to solve it. Someone give me a solution. Then, is there any method to evaluate this solution? How good it is or how bad it is?
Okay, so let me maybe paraphrase your question. You say, well, I already know this problem. It's traveling salesman problem. It's NP hard. Okay, and then I have maybe 1,000 cities traveling salesman problem. I want to find the optimal solution. I cannot. Okay, I don't know the optimal one. Maybe I ran my simulated annealing for 3 days. I get the acceptable solution. I say, well, here's the solution. And then maybe you give me another one. Wow, that's better than what I got. Okay, and then does that mean you got the optimal one? No, I wouldn't say so.
Yeah, I mean, there is any method to, do the performance evaluation.
What do you mean by performance evaluation? I can say, yeah, yours is better. So my simulated annealing doesn't tune very well. I will ask, what did you do to solve that 10,000, maybe 1,000 city traveling salesman problem?
For example, if I have this traveling salesman problem, someone give me a solution.
Okay.
They claim this is optimal.
Okay, that you can check, for instance.
Yeah, how to check?
How to check that? Well, for instance, you run simulated annealing for 1 day. You think it's already better than what the person provided to you on the solution. Then, of course, you don't believe that. You say, don't give me some crap. Okay, and on the other hand, if you say I already run my algorithm on the parallel machine for several months, but that's in real life, that's what people do, right? And then that solution still is better than what I got. Then, of course, I have every reason to believe, yeah, that's a decent solution. But does that mean this is the optimal solution to 1,000 city traveling salesman problem? No, I wouldn't believe so. There's no theoretical guarantee for claiming that. On the other hand, if the problem is formulated in such a way, like submodular function optimization, in that case, for instance, if I do my sensor management problem, I run my suboptimal algorithm, let's say, with the online bound, I say I'm 80% close to the optimal. I stop. And in the worst case, I'm at least 80% as good as the optimal one. And then if you gave me a solution, basically, I can evaluate. You can be better than mine, but probably if you say you can be 50% better than me, then I don't believe you. Basically, that's the difference. And David, you want to say something about?
Yeah, the problem I was working with mapping video frames and using matching points to try and improve the roll pitch yaw XYZ of the data of the camera.
Can you be a little bit closer to the speaker? I'm not sure if other students can hear you.
Sorry, can you hear me now? Can you hear now? How about now?
Well, maybe increase the volume a little bit if you want, if you can. Good.
Let me see if there's a volume for the mic on here. Yeah, I'm not sure. Is it any better now?
Yeah, I think a little bit better. Go ahead.
Sorry. Okay, so I tried to break my problem down into smaller pieces that I could approach. So I've got multiple video frames. I have match points between each frame, and I have some metadata to start with for each frame, but it's not very good. But it gives me an initial start for the roll, pitch, yaw, and the XYZ world coordinate of each camera pose. So what I did is I've broken it down into using something like fmin search, and my objective function is a Euclidean distance. So I project all of the match points just on a global basis, just looking for biases in the overall XYZ and the roll, pitch, yaw first, just to establish, because there are times when they may not have calibrated their compass, and there will be a consistent bias in the compass heading of the platform that's used to collect the video. Okay. So run it through this first, and then I go through all of the match points, and I find which ones are actually related to one another beyond the next frame, and then I use that information to come up with what I'll call relative ground control points. By taking the centroid of where they project to, if I know that they're all the same location on the ground, take the centroid of where they project to, throw out the outliers, and then use that centroid as what I'll call a ground control point. Now I have a set of ground control points, and I use that to go through from one frame related to the next frame and optimize just on that metadata. Actually, I stated that wrong. Optimize on the metadata of one frame at a time using my global set of ground control points, so that I'm forcing the metadata from one frame to agree with the metadata of the next frame, because I'm using this global set of ground control points.
Okay. Okay, so I guess for your particular problem, I still don't have the clear picture on how you can define a very meaningful objective function that actually, by optimizing that, you can do a good image registration across the frames and also have a better estimation on the bias, on some potential bias across different images. So I will look into your initial write-up and try to provide some feedback. But because it's not really my research field, I can only give you some very intuitive engineering suggestions on that. So basically what I realized that so far we talked about the optimization problem where we have to fully specify the objective function. We have to assume we can evaluate accurately and just find the mathematical tool to get to the maximal minimal solution. And in many real engineering problems, we don't have the luxury even to do that. Why? For instance, you may say even evaluating this objective function, you may have some constant noise coming into that, so that you don't have a reliable way of even evaluating the objective function. You may say, well, I evaluated many times and take the average. That may be good, but how do you optimize an objective function when each evaluation is considered noisy? And that's basically, I think, in real engineering problem, you may encounter that. So because of that, I try to change a little bit on my gear in terms of the course material coverage. Next time, I intend to talk about stochastic optimization technique. I think some of you may already learn that because you took adaptive filtering, which is close to what I'm trying to talk about. But still, my emphasis will be on optimization part, but try to at least cover some real engineering aspect, like for instance, the image may contain noisy observations, may contain outliers, and your optimization technique may need to calculate the gradient direction approximately, not always exactly. Can you still make sure that this gradient descent algorithm works when each step is considered noisy? I'm trying to talk a little bit on that one. But still, for those of you who don't have good background in probability theory and stochastic processes, the material would be a little bit abstract. So I don't know if that would be okay to all of you. But basically, that's my plan. Sarah, you have something to say about?
So we're going to talk about like MCMC and likelihoods and stuff like that.
Well, not to the level of Markov chain Monte Carlo method.
Oh, okay.
It's mainly, for instance, how you obtain stochastic gradient direction. How do you make sure that this is also meaningful when you try to optimize objective function in a noisy setting? And what are the engineering applications to that? So I will try to prepare slides and cover that material instead of talking about mathematical formalism in convex programming that has some variations in terms of convex function. Original problem may not be convex program, but after some transform, it may become so. By saying that, I'm trying to cover geometric programming or semi-definite program. And that, if time doesn't allow me to do so, I will, maybe another alternative would be talk about still combinatorial optimization, but the emphasis will be on greedy algorithm and also some sparsity pursuit techniques. I think some of you are interested in that, right? But I'm not sure about other students, so I have to really consider some balance.
So you won't talk the multi-objective
Multi-objective, you're interested in that? Okay, because that part, the mathematical formalism is unclear. What I can cover for multi-objective function would be, for instance, to the general level would be combine that to a single objective function. By changing the weights, you can actually partially recover so-called the Pareto front of your solution. And that, I think, in my notes on the genetic algorithm, I partially mentioned about this key idea. Other than that, of course, you can use like genetic algorithm or simulated annealing, even particle swamp optimization to calculate this Pareto front in order to make trade-off among different objectives. But I probably don't have time. I don't want to spend time on that because at the surface level, there's no good mathematical theory behind it. That's my main reservation to multi-objective optimization technique. Okay, so any other questions or comments? All right, so I guess we don't have new homework assignment due next week. So please think about what you want to plan to do on the term project. And also we do have new computer assignment you may want to work on. And also if you want, you can write maybe 1 to 2 page description on the project that you want to work on for this course, because that's a very important component to get your hands-on experience in real engineer optimization problem. I remember, I would hope that your description would be comparable to the assigned term project. So don't give me something too vague, and don't give me something that's too specialized, meaning that I have to invest a lot of time to understand your problem. For instance, the first introduction should contain adequate information on the background of your problem, not too specialized. For instance, maybe the first part is 10-page on underwater communication. That's too abstract. And if that's about, for instance, how to study bioinformatics in order to do some kind of isoform reconstruction, then it will be too hard for me to comprehend and make some meaningful comments. I hope that you try to make it understandable in layman's terms why this research is important, why you think this engineering problem can be formalized as an optimization problem. And also provide you initial attack what you plan to do to solve the problem and how the course material may help. And I hope that you try to at least do some literature survey and explore the state of the art optimization algorithms in order to pick the right tool for you. Okay, so that's it for tonight. And of course, I will stay here for a few more minutes, just in case if some of you want to discuss about the material or the project, I will be here. Thank you.